right, so I'll see you at noon online, okay? It'll be fun, like it was the last time. All right, let's get going.
All right, NFL 41 for the clicker question. You guys can get started now.
Which one? Which one's first?
Okay, relax. Whenever it goes, okay.
We're getting there, we're getting there. Here you go. Now I'm all set.
All right, you guys can get started now.
Wait, is this the first one? Ooh, with the acceleration, it's definitely going to be
Oh wait,
yeah, it's going to be it says like ortho, it's supposed to, the major product is either A or D, but I'm guessing it's A is no contact unless... Oh, it's not even a thing, is it? Yeah, it's not. Then why are you doing that? Unless the H2SO4 is an already
It's gotta be B.
Oh, yeah.
Well,
Yeah, sorry.
I was just looking at
It keeps saying, okay, sorry, yeah.
All right, think about another substitute.
So A or C? Is it A or D? Me too.
5, 2, and 1. All right, great. Yeah, so A was the correct answer. Looks like most of you made it there, so that's great progress for Wednesday. We're going to talk a little bit more about this today.
I thought it was a meta director.
In the meantime, let's go to the second clicker question, which I promised you a naming for reading ahead nomenclature.
I think it's B. Because the only reason it's the name B1. So that's it. Pheno and the boxes should be next to each other. And then I think it's B. This time I'm not going to get to it too. Sorry about it. Yeah, you're right. It's one of the It just is so weird. That's a clicker.
Take about 30 more seconds.
You do.
I did that.
I'm doing because it's like the functional group that's
Looks like most of you
required.
guys just
Yeah,
wanted
I'll call it.
4, 3, 2, 1. Yeah, it looks like you guys are doing really great today. The clicker question B was the correct answer.
Man, Chloe needs to be done.
Okay.
I don't know why you thought I was racist, but it said something like that the first week of school.
I think so, yeah. I think that's not a problem. I can give the clicker question
Raw.
for next minute. Can you guys hear me okay?
Yes.
Now that it's Friday, finally we got batteries for the microphone. Is it working or should I just try to be a little bit? You guys back there, you can hear me? Okay, thanks. And so it's Friday. You guys made it all the way to the end of the week. We're almost there. Nothing could go wrong today. I have my favorite sneakers and my cute Floyd shirt, so we're ready to go. And I also think I sorted out the computer issues the other day. What happens like when you don't update your computer, it forces you not to questions. I'll try to get those online so you can use them for practice if you like. How today is going to work is the first half of class, I'm going to talk about spectroscopy and nomenclature as promised, and then I think you guys might like to have a little more review from Wednesday, so I'm going to readdress some of the electrophilic aromatic substitution for Wednesday, and hopefully by the end of today it'll all be crystal clear. It was good to see some of you in office hours yesterday, and continue to go to Dr. Dixon the next week, and also with GSS and campus discussion. So those are the quicker questions. Okay, so everyone got a chance to look at the nomenclature over the last couple of days on these couple pages. Yeah. All the naming is essentially the same. All the same rules apply from previously when you named alkenes or alcohols. For example, you remember if you have an alcohol on an alkane or an alkene, the alcohol takes precedence, and so you would call that something like methanol. You change the ending of the name. The same thing is here for benzene, for example. So instead of calling this third one over here, benzene, we call it phenol. And you see some other common names are toluene, styrene, anisole. We worked with anisole on Wednesday. And I didn't specifically say it until later in the class on Wednesday, but if you're still wondering what was the ortho, meta, and para, that's an old way of naming things that we still use today. It indicates which way these two substituents are attached. And it only works when you have two substituents, not when you have one or three or more, only for two. And when they're placed right next to each other, that's when you have ortho. And so this molecule, for example, could be named either ortho-dichlorobenzene, or you could name it 1,2-dichlorobenzene. They're both acceptable names. Same thing with meta when you have them in this side. And by the way, it doesn't matter if the second fluorine is here or here. They're both still next to each other. That goes with meta as well. So if you put the NO2 group down here, that's still a meta because the benzene is flat, so it doesn't matter which side you put it on. This could be called meta-bromo-nitrobenzene. Notice that because you have both substituents here, you use in the alphabetical order. It's the same thing you do for all the rest of the naming. So BR comes first, so then you have bromo-nitrobenzene. Or you could also call it 1-bromo and 3-nitrobenzene. Then just as a last example with para, that's when you have them in the most distal position, or the furthest apart from each other. You can call that para-fluoroiodo, still alphabetical. Or you can name it the other way with 1-fluoro-4-iodobenzene. Down here on the bottom are some other common names. I'm not going to necessarily go through all of them. I just want you to be aware that there's some of the common names. So sometimes instead of saying, di-alcohol or talking about like 2 OH groups here or here, sometimes in literature you would see the word hydroquinone. And if you commit these molecules to memory, you would just be able to picture in your head, oh, this is what hydroquinone looks like, or this is what xylene looks like when you have 2 methyl groups attached. So some of these you should commit to memory. That's something you might see on a multiple choice exam, like label the correct name of the common names of the correct benzene structure. That's something that you might see. And again, with OH being the principal group, and the rest of it is the same as all the previous naming that you've learned. The example on the top right is the alcohol is the principal group, or it's the parent group. So now we will call it something phenol, and it would be either meta-nitrophenol or 3-nitrophenol. So it's pretty straightforward. Do you guys have any questions about that so far? Yeah, I think you guys got naming pretty well. We've seen it for 2 semesters now. The last example with nomenclature is now when I have 3 things. And you follow it's the same rules. So you do alphabetical, and then you do it with the lowest numbering. So once I have BR is the alphabetically first, so I'm going to start my position 1 there. And then I'm going to number it so I have the lowest numbers around the ring, which turns out to be 1-bromo, 2,3-dichlorobenzene. And then looks like a 2-ethoxy 5-nitrophenol. That was a quicker question for today. So it looks like you guys did great with that. Actually, this is the last thing I want to show you. There's a small, it's a subtle difference, but it's something I want you to be aware of as you are going through organic chemistry and maybe even reading some of the literature. You can sometimes, well, for the rest of the nomenclature, everything was something benzene. nitrobenzene, bromobenzene. Sometimes the benzene ring is actually a substituent in itself, kind of like a functional group to the rest of the molecule. For example, on the left here, this is called dibenzyl ether. So you're using ether as sort of the main name of the molecule, and you are taking the benzene ring now as the side group. And there's two ways that you can name the benzene ring. One of them is calling it a phenyl group, and that's when you only have the benzene ring and you don't include anything else. So for example, that would be called diphenyl ether. But when you have the aromatic ring and you have a CH2 group sticking off of it, that's when you change the name from a phenyl to benzyl. So the name of this molecule then would be dibenzyl ether because it includes not only the ring, but that CH2 group is there as well. So that might be something you could see as a multiple choice question or something like that. What's the difference between a phenyl group and a benzyl group? It's subtle, but it's important to note. Any questions about nomenclature before I go on to spectroscopy?
Could you go back one slide just
Yeah.
for a second?
And you?
What if you add like another C to like the benzyl group?
Then, so if you wanted to add on to the benzyl group, you would still consider, going back to that previous slide, you would still consider that blue box as the benzyl group. If you added other carbons, that would be a different part of the name, and it wouldn't change the fact that it's a benzyl. And then you just wanted to write something down, or you had a question?
I just wanted to see.
Oh, yeah.
When it comes to priority and naming, I see you did either, like what makes the benzyl group, the benzene a substituent? Like naming wise, priority, is it ether, then benzene ring, or are there things on top?
Yeah, so that's a good question. You kind of follow the same general rule that you have the whole time in organic chemistry 1. So there are times when the whole rest of the molecule, like for example, if you had a really long carbon chain and then a benzene ring at the end, instead of calling it something benzene, then you would maybe call that a substituent, like something phenyl instead, or something benzyl. It would actually be benzyl with the rest of the carbon chain attached. So it just depends. Let me think of a better example, and I might get back to you on that. It's a good question. Okay then, so I'm going to go over IR spectroscopy and NMR, and then UV vis, and then we'll go back to the substitution reactions. So for IR, the one thing I want you to remember, or that you should remember, is that the benzene ring has 2 unique stretches. And that's because when you normally have just a double bond, let's say like ethene, then you know the bond order for this is 2, right? If you are calculating the bond order as bond order of 2. And if you have just an alkane chain, it has a bond order of 1 between the carbon and the carbon, right? But you see the benzene ring, it has this sharing of pi electrons around the ring, so it's actually delocalized, and your bond order is what? Does anybody know?
1.5.
I think I heard a 1.5. Somebody? Yeah, it's 1.5. So even though we draw the bonds like this, oftentimes you'll also see the benzene ring drawn with a circle around it. That's just to indicate that these bonds are shifted in places. So this double bond doesn't stay here. And this bond isn't shorter than this single bond. They're all the same length. And these pi electrons are continuously moving around the ring. So it has a 1.5 bond order. So because the bond order is different, it's going to stretch and wiggle and bend a little bit differently than if it was a pure single bond or a pure double bond. So in that case, if you look at the stretch, the CC stretch around 1500 and 1600, that's usually unique of something like a benzene ring. And that's something you can look for. So if you see a stretch like that in IR, then you can go directly to your NMR and see if you also see peaks in the proton region that correspond to a benzene ring. That will help you hopefully solve the molecule. Okay, so when you're talking about proton NMR, you notice that the phenyl rings have protons that are more in the 7 to 8 part per million region. So rings with protons, 7.1 part per million, and those pertain to these 5 protons here. Does anybody know why those are shifted farther downfield, you guys already know that for alkenes, usually it's between 4 and 6, or 5 and 6 for you see alkenes. So why with the benzyl group does it show between 7 and 8? Yeah.
Sorry, when you said that there were two unique stretches, did you mean there was one at 15 and one at 1600?
Yes.
Okay.
Yeah. So you have one at about 1600, and you have another stretch at about 1500. You have two unique ones. So does anyone have any idea of why maybe these protons are shifted even farther downfield or far from home? Home being 0. All right, so then I'm going to go over that. It turns out that the way the benzene ring is shaped, you have, remember the pi orbitals that are above and below the benzene ring? So you have all your protons here. Right, so remember your sp2 orbitals? So essentially, when you have this ring, you create a ring above the benzene ring and electron density below the ring. That creates what's called ring current. And so the benzene ring has this ring current around it, and that actually induces a field. And the field is drawn in pink. So because of those orbitals that give electron density above and below the ring, you're going to have this pink current or electric field that's induced in the ring because of this ring current. And then if I'm doing NMR, I'm going to apply a fairly strong magnetic pulse to that. And so when I add in my blue magnetic pulse, you can see that half of the circles going down into the center of the ring, they're opposing that magnetic force. So that those like cancel, so to speak. Not exactly cancel, but they're in opposite direction. But if you look at the ones where the protons are, the arrows are pointing up on both sides. And that's kind of an additive. So you have an electric field force going this way, and the protons are all on the outside where the ring current is having the field go up also. So for that reason, it causes the protons to become more de-shielded, and in order for them to resonate, they have to show up further downfield or at a higher frequency. So you see, for example, this para-benzene molecule, you have the protons for the benzene ring that show up between 7 and 8, which is further downfield. Okay, so if you see protons or you see resonance structures between the 7 and 8 region in parts per million, then chances are you have a benzene ring. In fact, it's pretty much a given that you're going to have that. Then you just have to figure out, well, what kind of a benzene ring do I have? Is it substituted? Does it have 1, 2, or 3 groups attached to it? And not only how many groups does it have, but which way are they attached? One example that's shown here is when the groups are attached to para. So the ethyl group and the bromo group are farthest apart from each other, and that's para. And I gave this example because it's the easiest one to see the type of splitting you're going to get in the resonance structures. When you have para-substituted benzene, you're going to get this called doublet of doublets, and they're going to be leaning into each other. So if you see something like this on your homework or an exam, you would be able to tell that I have a benzene ring and it's para-substituted. Now if it's substituted in ortho or meta, depending on the substituents attached, the splitting gets a bit more complicated. So you can, sometimes you can be able to deduce whether it's a meta or an ortho, but if it doesn't look like a doublet of doublets, you know you have one of those two. If it looks like that, you know your molecule is a para, and you can start from there. Also notice that because of that same ring current effect, that the CH2 group that you would normally expect to be somewhere between 0 and 1 or 0 and 2 is now actually at 2.5. It's also being de-shielded for that same ring current thing that the last slide I showed you. So that CH2 group is further from home, and the CH3 group doesn't feel that ring current so much, so it's closer to 1. Are there any questions for that? Yeah. Good question. So these leaning doublets are created these two protons on the left, they're labeled A. I don't know if you can see that in the back, but it's labeled A here and A here. That's because those two protons, they are the same as each other. They're both next to a proton and they're both next to a bromine. So that's why one of these peaks shows up representing those HAs. And it's consequently the same thing for HB. On the top is next to an ethyl group and it's next to a hydrogen. And this HB is next to an ethyl group and it's next to a hydrogen. And so it's going to have its own peak. Now, the splitting part comes from that leaning is because you actually have some amount of coupling between the A and the B, that they're next door to each other. And so this coupling causes this, instead of having equal doublets, like we talked about in the beginning of the semester with spectroscopy, they're going to be a little bit leaning inward. And this is because of the ortho coupling you see. And by ortho, I don't mean that the substituents are ortho to each other. I mean that the hydrogens are now ortho to each other. And a good example, or another example of that, or clarification for that, is this table on the right. So when you have two protons that are ortho to each other, they're going to have some splitting where the peaks are split between 6 and 10 hertz. Remember that hertz is the frequency, and part per million is also a frequency. It's just in different units. So usually on the NMR baseline, you see parts per million. And then when you talk about this J coupling, it's listed in hertz. But really, it's just a unit conversion between parts per million and hertz. So for parasplitting, it's between 6 and 10. And in this case, you can see each of these peaks, if you measure the distance, they're both going to be 8.4 hertz. And that's when those protons are ortho to each other. If the protons are meta to each other, then that distance between the resonating peaks, they're not going to be 8.4, they're going to be much smaller, closer to 1 to 3 hertz, so much closer together. And then you can see for para, they're even closer together in terms of having splitting. Does that help to answer your question? Yeah? Okay. Do you guys have other questions about NMR or IR? Should I go on to the electrophilic aromatic substitution from Wednesday? Alright, I'm going to go there and I'm going to start from the beginning and stop me if you have any questions. Okay, so we already went over on Monday you can have electrophilic aromatic substitution, and that's shown with the top, with the proton being substituted with a new electrophile. And then on Wednesday, we said, well, if we have an electrophile on our benzene ring already, how do we add on a second group or a third group? And I boxed ortho and para because they're always paired together. So if I have a second electrophile that's going to come in, let me rephrase that. If your original electrophile, so the one that's not primed, if it's an ortho director, it's also a para director. So you could get both products, an ortho product or a para product. They work together as a unit. And if your substituent directs ortho, it's always going to direct para. And if it directs para, always ortho. It will never go meta. Conversely, if you have a meta director, so your original electrophile would prefer to add a second electrophile in the meta position, it's always going to be a meta director. You'll never see like nitro group. We talked on Wednesday about nitro groups being meta directors. Never ever will you see original electrophile being a nitro group directing anywhere but the meta position. And that's what I'm going to show you why for resonance. And you had a question?
Yeah, is there ever a case where the ortho product would be the major product versus the para product?
I don't think so. It's probably not impossible, but because anytime you have that ortho substitution, you're going to get those van der Waal interactions. And so you may get really close to 50-50. It's tough to say experimentally, but for now, no. Okay, so this is the same slide I showed on Wednesday, and I think today it makes a little bit more sense. So if you're adding on the second electrophile, it can go ortho-para, or it can go meta. And not only could it go in ortho-para or meta, but it could also go faster or slower than the original substitution. So if my original substitution at the top was at H going to E, if that goes at, let's say, a rate of 10 miles per hour, if I'm adding my second electrophile, which is the same reaction, let's say I brominated the top, and I want to brominate it again. Does that second bromination happen at a rate that's faster than 10 miles per hour, which would be activating, or slower than 10 miles per hour, which would be deactivating? And that's the only difference between activating and deactivating. Now I know they're not actually moving at miles per hour. They have rates and rate constants. But that should give you an idea of it being able to identify the difference between activating or deactivating. It's all based on that original benzene. Does it happen faster than that, the second reaction, or does it happen slower than that original benzene reaction? And how these happen boils down to the resonance and inductive effect of their original electrophile. So depending on what electrophile you have and its resonance or inductive effects, that's what's going to give you activating or deactivating an ortho, para, or meta. How are we doing so far? Any questions? Great. Okay, so here's that table that I was trying so hard to show you guys on Wednesday that hopefully you already saw on page 763. So at the top of the table, listed in pink, you have the ortho and para directors. And you notice, and maybe you remember from Wednesday, that ortho and para directors are two things. Either they have a lone pair of electrons they can donate, or it's an alkyl group of some sort. Also, it includes the halogens as well. So you see the top half of the table has an amine that has a lone pair of electrons, hydroxyl group, lone pair of electrons, an ether group, an amide group, an alkyl group, the ester group. They all have this one thing in common, and that's a pair of electrons to donate that electron density into the ring. Right? Because think about when you're doing these substitution reactions, every time you're forming that carbocation intermediate. And your goal is to form the most stable carbocation intermediate so it has the lowest energy of activation. And any of the ones that have lone pairs are able to donate their electron density to stabilize the carbocation. Now, if you look at the ones on the bottom, the meta directors, you see they don't have any lone pair of electrons, and they're not just pure alkyl groups. And in fact, the ones that are meta-directing have some sort of dipole or actual formal positive charge on them. And I'm just getting ready to show you some examples of that and do some work on the board to show you. One last thing about this table, and I'll come back to it in a minute, but fortunately, and it makes it easier to commit these to memory, is that all of the ortho and para directors, the alkyl groups or the ones with lone pairs attached immediately to the benzene ring, they're all activating. So you know if it's ortho-para, it's going to be activating. So those go hand in hand, except for the case of halogens. You know, if halogens are right in the middle, they are deactivating, which means they will go slower, but they still go ortho and para. And you know all the time, hands down, if you're doing a meta, or you have a meta electrophile come in the meta position, all of those are going to be deactivating or slower than the original benzene reaction for the same thing. That is an example of a polar group for meta. Okay. So now I'm going to show you exactly why some of the alkyl groups and why the lone pair of electrons cause something to go ortho and para, and why it's not favored to go meta. If we take toluene, for example, and I want to add bromine to that, or let's say chlorine. We want to add Cl2, so we'll use FeCl3. Just like for bromine, we just switched it out for chlorine. So you have your first reaction that you guys got on Monday. So I won't show the mechanism for that unless you want to talk to me after class. Oh, wait, So this part, I'm not trying the mechanism for. We're just starting here. If you want to see that, come see me afterward. Now, if I have this first methyl group and I want to add on the chlorine group, how do I know where it's going to add, right? You're trying to do your homework and you're trying to take the exam, and you need to know where it goes. So let's say I don't know where it goes. And so since I don't know, I'm going to put it in the meta position just to pick one, because you have to start somewhere. So this is the meta position, and my carbocation is going to be here. So once you've formed your carbocation, your next step is to draw those resonance structures. Okay, I think I kind of went down the board a little bit, but hopefully you can see all the resonance structures. I hope that you guys can write in a straight line your notes better than I can on the board. But nevertheless, you see I have a secondary carbocation and a secondary carbocation and a secondary. So that seems fine, right? Because secondary is, I mean, that's okay. But now before I make my final decision on what my major product should be, before I say, yeah, it's definitely going to be a meta product for sure, you should also draw the resonance structures for ortho and for para. So the para is up there. I'm going to draw it for ortho. That's right. And draw your third resonance structure. Okay, so now I have resonance structures for para substitution, ortho substitution, and meta substitution. So since I drew the ortho one on the board, can anybody tell me what the difference between the ortho resonance structures and the meta resonance structures?
Tertiary.
Tertiary, right? So if you look at the resonance structure, you go around and see, just trace where the carbocation goes as you have your resonance structures. You see this is a tertiary carbocation, much more stable than a secondary. And yes, this one's a secondary and that one's a secondary. But if you try to put your second electrophile in the meta position, you see it's secondary across the board. So even though a reaction would occur if you had secondary across the board, if you had a choice of which one to make, of course you would want to substitute at an ortho position or the para position because you'd be forming an intermediate that is more stable. That means that your reaction energy diagram is going to have a lower energy of activation if you're trying to substitute in the ortho or para, and you have a higher energy of activation, the delta G, if you're trying to do it in the meta position for this type of reaction. Does that make a little more sense? Do you guys have any questions about this one? So I just showed a second example up here, which was trying to put it in the meta position, and it's the same thing I have on the board, just to show that it's a less stable carbocation intermediate. All right, so then another example would be if I have a meta-directing group. So how do I know when it's going to be a meta-directing group and not an ortho, and why is that? Okay, so that's a nitro group. I guess we can stick with that. But it's any group that has a dipole moment or has a positive charge on it. add that complexation. So either one you want to draw is fine. You could draw it shown this way, and that's fine, or you can draw it shown this way, and that's okay too. So let's say I don't know where to put my product, right? You're taking your exam, you're working on your homework, you're trying to figure out, I don't know where the second group is supposed to add. And that's okay. Just pick one and draw the resident structures, and then draw the resident structures for all of them. That's what we'll do. So I'm just going to pick it to go in the ortho position. Okay, so there's your first carbocation intermediate. Now your job is to draw the resonance structures. So try to get them in your notes while I'm drawing it on the board. Okay, so hopefully you have the same three resonance structures in your notes. Does anybody see anything in particular about this resonance structure that you maybe don't like? Yeah. Yeah, look at the first resonance structure I drew right there. Yeah, two positive charges next to each other? No, thank you. That's way too high in energy compared to the other carbocation structures. So if you look at the slide over here, if I added it in the meta position, my three resonance structures is all secondary, secondary, secondary. Same thing over here, they're all secondary carbocations, but in this case, I don't have two positive charges going head to head to each other. That's why if I have something with a positive charge here, or even a partial positive charge, right, with those acyl groups. Remember from that Friedel-Crafts acylation? Even this you would expect to, when you add in your second electrophile, it would absolutely add in the meta position. Doesn't matter if it's this one or this one, but it would go meta for the same exact reason. Because this has a dipole. And so this is going to have a partial positive and a partial negative. And you don't even want a two, partial positive and a full positive. You don't want anything too, you don't want the positives being close to each other. So for this reason, when you're doing a reaction to add electrophile to this, even this will add to a meta position. Do you guys have any questions? Does that help? Is it a little bit more clear than Wednesday? Kind of makes some sense. Okay. So of course on the bottom, I just drew an example of the para. So you have it in the ortho, we drew up here, and in the para, you see the exact same thing happens, where you get the two positive charges next to each other, and that's less favorable. So you look at that energy diagram, look at that, the activation energy diagram. The ones for ortho and para are going to have a much higher energy of activation than simply the ones for meta. So the last example I want to show you is with, before I showed you with an alkyl group, but what is it about those lone pairs that make the second electrophile add in the ortho or para position? Before I draw the mechanism for this up here, does anybody remember the name for that molecule? The one on the left?
Anisole?
Yeah, anisole. So I heard a couple of you guys see it. That's great. So I'm going to start out with anisole, and I want to add a chlorine to it like I did before. And I'm trying to figure out which way it goes. Then I'm just going to pick one. So for example, I did ortho before. I'll go ahead and put it in the ortho position again. Yeah. This one? Not in this case that it's going to show any benefit for the carbocation stability. You could technically take a pair of electrons from here and move them up here, but that's not going to help your carbocation stability. Okay, so going back to over here, have it in the ortho position. And that makes my carbocation here. So now draw your resonance structures while I draw mine on the board. So how many total number of resonance structures do you have if you reacted in the ortho position here? 4, right? So you have 4 different resonance structures that you can draw. So that means you have 4 different ways you can stabilize the carbocation, which is more ways than you would if you tried to react it in the meta position. And the real key here is this 4th one. So all the others are the same. Secondary, 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 the same thing you would get if you had meta carbocation intermediate. But here, because you hadn't take that pair of electrons and donate the electron density around the ring, it will help to stabilize that carbocation, and then this one will have a lower energy of activation compared to if I tried to put my electrophile in the meta position. Which would give me the same exact thing as the resonance structures on the bottom there, except for instead of a methyl group, you would have the OCH3 group. Okay, so do you have any questions about the ortho para versus meta directly? No questions. See, I see your head shaking now. So hopefully this makes a lot more sense. That's really the whole package, right? So this is electrophilic aromatic substitution. You have those 5 basic reactions. Of course, there's more, but in the scope of this course, the initial 5 I showed you on Monday. And then you can take any of these groups. So technically, if you look back at this table, I could put any of those groups onto the benzene ring. And if I give you any of those for your homework or your exam, you should be able to say, okay, if I want to add a second one, where is it going to go? And is it going to go faster than it would if it was benzene alone, or would it go slower than if it was with benzene alone? And that's electrophilic aromatic substitution. So if you can figure that out and you can do that, then you'll be just fine.
We have 5 minutes.
That's true, there's 5 minutes.
All right, here we go. So there are 4 trailing reactions that we need to know. So here we go. Once we get on to once we make are 4 trailing reactions that we're going to need to know that we're going to talk about today so that we can jump right into synthesis on Monday. Okay, so the 4 trailing reactions are as follows. You all know how to go from benzene to sulfonobenzene, right? Or benzene sulfonic acid. Okay, so one way that we can go now make phenol is do something like H plus and OH minus. Just a little acid-base workup is going to change sulfonobenzene to phenol. You don't know a way to make OH as a great electrophile, so this is a way to make phenol. Because phenol, that OH, is generally a nucleophile. We don't see it as an electrophile ever. So this is number 1. Number 2 is to take something like benzene and make an alkyl benzene. One thing you should be curious about, and we can have a competing, sort of strategy with MS's class, is you can't really make toluene very efficiently from benzene itself. Okay? You should question that. Question that over the weekend. We'll ask that question as a clicker question on Monday about why that wouldn't be such a good strategy to do. But if you work here, you'd be working through a Friedel-Crafts reaction to get now the isopropyl group on there. We can take any benzene that has one benzylic proton, a singular benzylic proton. This example does have only one, and that's all you need is one. So toluene would work. If you can make toluene, you could do this with toluene as well. But you can make benzoic acid from this. Benzoic acid comes from an oxidative reaction with KMNO4. So now you have to be careful. If any of your molecules have benzenes and benzylic protons, that's going to kill it right back to benzoic acid. So you got to be very careful with your permanganate and chromium species when you're working now with this. Okay? The next one is going to be to get from nitrobenzene to aniline, which also aniline is an amino group. An amino group then cannot be very easily derived into a electrophile to be packaged in this unit. So what we do is we work with tin and HCl to get us from nitrobenzene to an amine. Okay? So we've now made aniline from that nitrobenzene. And there is one more. Why can't I think of what it is? So we have an acyl. Oh, I know what it is. Here we go. And the last one is a reaction that you actually will know. Figure out how to get there. You will know the actual mechanism for come the next chapters. Okay, and this is what we would call a reduction. In this case, you form a hydrazine, or hydrazone, I guess you would say, and then you react it with base. And this is going to give you now the reduced carbonyl. Okay, so everyone see that that carbonyl is just gone. It's become a CH2. Okay, so all of these intermediate steps you know how to create because of Caitlin's great work this week. The sulfonobenzene, the isopropyl benzene, the nitrobenzene, and now your acyl substituted. But these 4 trailing reactions are going to help us in synthesis. Yeah?
What are those reactions before?
Oh, this is